for me as Aswena from ECE31 and welcome back to my YouTube channel. So for today's vlog, we will be discussing about the Summative Assessment 1 for Power Electronics lecture subject. So for today's summative assessment, we are required to use PSpice to determine the instantaneous and average power in the given problem below. And this is the problem. So a current of 5 sine 2 pi CT amperes enters an element. We need to sketch the instantaneous power and determine the average power absorbed by the load element when each of these elements will be given on the circuit. For our condition A, we will be connecting a 5 ohm resistor. For condition B, we will be connecting a 10 millihenries inductor. And lastly, a 12 volt source current into the positive terminal. So with that, we need to create a new project. And then let's type the name of our project here as Summative Assessment number 1. Which is for our LX, and we need to click OK, and then we need to create a blank project. So let's just wait for it to load up, and then this will be our area for our schematic. So for our first component, so before proceeding with the creating of our schematic in PSpice, later on I will be showing and explaining the calculations for the theoretical values for each of the conditions so that we will be sure that it will match our measured values using the PSpice. So if you can still remember, our given is an AC current having a value of 5 sine 2 pi CT. So considering the AC value of that, we will be placing a component, which is our current source, which will be giving the circuit an AC current supply. So let's search here current sign. So we will be choosing between the two, which is a sine wave or a transient sign. So we will be choosing the transient sign current source to satisfy our circuit requirements, which is to provide a current AC source which is connected to a 5 ohm resistor connected to a ground. So the value of our resistor is 5 ohms. And let's not forget our grounding. So let's put 0 capacity on our circuit. So please take note that this should be 0 so that the circuit is with proper grounding. So let's connect our circuit here. So let's connect it with our wires. So here. And the other one is here. So let's connect all of the components here. So this will be our components. So let's zoom it. Going back to our given in the problem, it is noted that the peak amplitude of the AC current is 5 and our frequency is 60 Hz. Then, taking note of our lecture from our previous subjects in AC circuits, frequency is given, we can compute for the period, which is 1 over frequency. So here in the given, the period or T will be 1 over 60 or will be 16.67 milliseconds. So you have to take note of that number because we will be using it in our PSpice AC current source. We have to set I off to 0. Click OK. We have to set I amplitude to 5 because it is the peak value. Then we have to set the frequency to 60 Hz. After that, we have to click New Simulation Profile and then let's have our name as Summative Assessment 1. Let's have it resistor because this is for the resistor circuit. And then let's create the simulation profile. And then there will be a pop-up here. So we will be adding the run to time. So I said a while ago that you have to take note of the 16.67 milliseconds value. That will be our run to time, which is from our frequency, computing for the period, which is 1 over 60, that will give us 16.67. And converting this to seconds, this will be 0.01667 seconds. Since we selected a transient response for the current source, we will be selecting time domain transient for the analysis type, and then the start saving data will be 0 seconds. Then click apply, and then let's press OK. Then after that, let's run our PSpice simulation. Okay, there will be a pop-up here again. So let's just maximize our screen. Okay. Then let's add our traces. For the instantaneous power, we will be adding our trace, which is WR1. Okay. And for our average power, we will be adding our trace as AVG, or meaning average, and then parenthesis. And then let's click here our WR1. So let's click OK. So this will be our graphs. So for the green waveform here, this is for our instantaneous power. And then for our red waveform here, this will be for our average power. Now to get or to measure the peak value of our instantaneous power, so we will be turning on our cursor. And then we will be measuring the peak of our instantaneous power waveform. So I suppose this is the peak. So here in my end, as you can see, the value of our instantaneous power is 124.917 amperes. Now this time for our average power, so this is for our red waveform here. So we will be measuring the average power up until the end of our duration time, which is here on the end. So here in my end, the average power measured is 62.945 watts. So that's our average power. So for our condition A, this is our AC waveforms for our instantaneous power as well as our average power when an AC current source is applied to a resistive load and both are connected to the ground. So to prove the legitimacy or the correctness of our simulation in PSpice, we will be comparing our measured values here in PSpice to our computed values or theoretical values manually solved. Compare the value of our measured to the calculated values to verify the correctness of our results. Our measured values for instantaneous power is 124.95 watts compared to our calculated value, which is 125 watts, that I will be explaining later on how did we come up with that calculated value. Second, we have the average power by the resistor load, which is equal to 62.906 watts compared to 62.5 watts calculated, which both mark a minimal significant difference in the values when we will be computing their percent difference. So as demonstrated, this is the Orcad PSpice simulation results. And for the measured values, this is from our software. Then for the calculations of our theoretical values, we will be considering that the voltage across the resistor is current times the resistance. So given the current from the problem and then the value of the ohms, we will be having the voltage across the resistor, which is equal to 25 sine 2 pi ct. Now, we will be needing the voltage across the resistor to compute for the instantaneous power, which is the power delivered to our resistor load. So it will be voltage across the resistor times our AC current source. So that will be 25 sine 2 pi 60t times our current, which is 5 sine 2 pi 60t. So our instantaneous power gives us an equation 125 sine squared 2 pi 60t watts. So we will be considering the peak value, which is 125, which is correct with our measured values, approximately 125 watts. So for our average power, we will be using the principles or the formula learned from our power electronics lecture. So our power average is equal to 1 over t times the definite integral of 0 to time duration times our instantaneous power dt. And then the challenging part here is that we will be performing integration in this given equation. So if you can still remember the trigonometric identities that we used in our basic calculus subject, so using this first half angle formula for our half angle identity, we will be able to integrate the given equation above. Okay, so sine squared theta is equals to 1 minus cosine 2 theta over 2. So this is that part. And then we have to integrate the integral from 0 to 16.67 ms, which is its definite integral. And then after that, we will be evaluating the values, meaning we will be substituting the definite integral 0 to 16.67 ms to our t. Okay, so simplifying, this will be the final equation. And then we have to get the magnitude or the value of each of the equation to come up with these values here, which will be multiplied, and then with that, we will be able to come up with our average power across the resistor load, which is 61.45 watts, which is in minimal difference with our 62.906 watts here. So for an easier approach or solution for the average power across the resistor load, we can actually use some concepts from our AC circuits from our previous semesters. So Note that the average AC power is found by multiplying the RMS values of both the current and the voltage. So considering this equation, V times current times cosine theta, where theta is equals to 0. So we will be getting the RMS value of the voltage and the current, which give us this numerical values. And then after that, let's use this formula V times I cosine theta. So V times I times cosine theta. And using our calculator, we will be heading to this numerical values wherein cosine theta is equals to 1. Setting the angle of your calculator to degrees, and thus giving us the value of the average power, which is 62.5 watts in total. So that's the part 1. This proves that for a resistive load, for an AC current source, the instantaneous power is almost doubled that of the average power, because average power considered the RMS values of both the voltage and the current. Our part 2, we just have to maintain the circuit. Except for this load here, which is the 5 ohm resistor, we will be replacing it with our inductor here in series with our current AC source. So let's just replace our inductor and let's connect it in series with our current source. And let's just delete some unnecessary wires here for proper connection. And then based on our problem, the value of our inductor is 10 millihenries. Okay, so this will be the circuit for our part 2. Then we will be running the simulation. So again, there will be pop-up here in our screen. So again, let's just drag our screen here. So now again, let us add some traces. So we will be getting the instantaneous power on the inductor. So we need WL1, so add trace. And then for the average power, we will be getting average and then parenthesis, just like what we did on the earlier experiments, and then close parenthesis. And then this will be our output waveforms for the instantaneous power, which is the green waveform here, and the average power, which is the red waveform here. Now to measure the values of our instantaneous and our average, let's turn on the cursor and then let's draw from here. Again, our goal is to get the peak value from the green waveform. So here in my end, the peak value is approximately, from the graph, our peak value is 47.204 for the instantaneous power across our inductor. And now for our average power, let's turn our cursor on and then we will be measuring our average power up until the end of the output waveform. So here in my end, the average power across the inductor is 63.812 milliwatts, or if you will be converting it to watts, it's almost 0.063.812 watts. The correctness of our measured values using the PSpice. So we will be comparing it to our calculated values, wherein our measured values for the instantaneous power is 47.204 watts in comparison to the 47.125 watts calculated using our power electronics lecture principles. So explaining to you the calculations for our instantaneous power. Instantaneous power can be computed using this formula, I times the voltage across the inductor. The voltage across the inductor can be derived from this formula, L di over dt, which will give us an equation, I, which is the given from our AC current source, times L, which is 10 millihenries, times our current with respect to time. So simplifying our equation and multiplying the numerical values, it will give us 30 pi or 94.25 sine squared 2 pi 60t. So since sine is raised to 2 or it is squared, we have to apply a basic calculus trigonometric identity, which we can identify as double angle identity, wherein sine squared 2 pi 60t is equals to 2 sine theta cosine theta. So giving us the equation, we will be substituting 30 pi or 94.25 sine 2 pi 60t times cosine 2 pi 60t divided by 2. Getting the reciprocal of 2, then multiplying it to our denominator, this will give us this equation. And then simplifying or dividing 94.25 and 30 pi by 2, it will give us 15 pi or 47.125 as our peak value, which will be our calculated value for our instantaneous power. Now, for our average power by the load or by the inductor, we measured as 0.063 watts from the simulation, which is quite small compared to our expected values. And this matched our calculated value, which is 0 watts. So explaining to you the calculations for our calculated value, which is 0 watts, the average power can be computed using our AC circuit principle, wherein the average power is equal to the voltage across the inductor times the current, considering that these two parameters is in RMS value. So We have to take note that in an AC circuit of an inductor, the current lags behind the applied voltage by pi over 2 radian or 90 degrees. Thus, this gives us a phase difference between the voltage and the current, which is 90 degrees. So, substituting our values, so we have our voltage, okay, given, and we have our current, but you have to take note, okay, using our AC principles, that cosine 90 will be equal to 0. So any value that you multiply to cosine 90 will give us a value of 0. So the average power across the inductor will be 0. This gives us an idea that a pure inductor, meaning there is no resistance in series with our inductor, just like in our simulation. A pure inductor has a 0 or no internal resistance within its coil. This is for ideal conditions like with our simulation. So there will be no power across the inductor if it is an ideal condition. Thus, taking note of this, if it is a pure or ideal inductor with 0 or no internal resistance, this will lead us to minimal or almost no power on the inductor load. So that's our part 2. Our third condition wherein there will be a 12 voltage DC source connected to our circuit. So let's place another component here. So that will be a 12 volt DC source. So let's place another source. This will be voltage source and then DC. So we will be connecting it in series with our current source. Let's escape and then let's connect the component again. So we will be editing the parameters of our DC voltage source, wherein we will be setting it to 12 volts DC as stated by the problem. And then now that will be our circuit with the same time duration and the same transient response. So let's run our simulation. So again, let's add some traces. So our first trace is the instantaneous power across the 12 volts DC source, and the next trace will be the average value of our power across our 12 volts DC source. So let's just type it correctly so it will not be an error. So as you can see on the waveforms, the green waveform is the instantaneous power across the 12 volts DC source, and the red waveform is the average power. So if we need to invert the sign of our average power, so it will be correct in terms of our measured values. So now, measuring our values, let's turn on the cursor, and then let's first measure the peak value of our instantaneous power. So here in my end, let's measure it correctly. So here in my end, I measured 59.829 watts for the instantaneous power. And then after that, we will be measuring the average power, which is here on the end of the graph. So here in my end, I measured 9.93193 milliwatts, or we can say, or we can round it up to 0.001 watts, verifying the correctness of our measured values. So for the PSpice simulation, we measured 59.829 watts for the instantaneous power compared to 60 watts of our calculated instantaneous power. So this is our PSpice simulation results, and this is our measured values. So for our solution for the instantaneous power, we just have to multiply the current supplied on the circuit times the voltage across the DC voltage source. So our current is 5 sine 2 pi 60 p amperes times the DC voltage, which is 12 volts. So this will give us 12 times 5 is 60 times our sine 2 pi 60 t watts. So we will be considering the peak value, which is 60. So this gives us our 60 watts calculated value. Now, for our average power by the DC voltage load, we have here our measured is 0.001 watts. So here in my end, this gives us here 9.3193 M. So converting it to watts, it gives us a rounded value of 0.00 watts compared to our calculated average power, which is 0 watts. Explaining to you our calculations, let's direct here. So first, we will be getting the average current across the DC voltage source through this formula from our lecture discussions. So now, giving us the definite integral of this equation, we have to integrate. I hope you can still remember that the integral of sine 2 pi will be negative cosine 2 pi 60. Then we will be considering a correction factor of 1 over 2 pi 60 to balance our integral equation. So we will be substituting the value of our definite integral from 0 to 16.67 milliseconds to our simplified or integrated equation. So this is our integrated equation. And then using our calculator in degree mode for our angle, we will be getting these numerical values here for this part. Okay, so for this part. And we will be getting 6.28 when we compute or multiply these two values, the angle of our cosine, and we will be getting -1 when we multiply 0 to our degree here, which is 2 pi 60, and cosine 0 is equals to 1. So this gives us negative 1. So computing, so negative cosine 6.28 when inputted to the calculator is negative 0.9939. Then negative minus negative is equals to positive 1. And then this value here will be cancelled. It will be equated to 0. And numbers multiplied to 0 will yield us a 0 ampere. And then calculating for the average power, we will be using the voltage across the DC voltage and then multiplied it by our solved average current value, which is 0. Any number multiplied by 0 will yield a 0 result. So our average power for the third condition is 0 watts. So this is because in one half cycle, the source absorbs power, while in the next half cycle, it releases power. So that's the principle behind our third condition. Conclusion. Using our Orcad Lite software, we are able to measure the value and understand the instantaneous and average power of a circuit supplied with AC current. We explored varying type of load elements and the differences that each element brings to our circuitry. Also, instantaneous power equals to the voltage multiplied by the total current, while the average AC power is the product of the RMS values of the same two parameters. Moreover, we can say technically that the average power of the inductor and DC voltage source, both connected to the AC current source, is 0 because when AC current is applied to an inductor, the current lags behind the voltage by 90 degrees. And lastly, for our applications, overall, knowledge about AC power as well as the effects of different elements connected in a circuit is helpful for electronics applications requiring the control of power delivered by a circuit to meet project and devices' power requirements. So again, my name is Ricami S. Casabrena from ECE31, and I hope you learned something from our power electronics vlog for today, and I hope I will be seeing you in our next episode. Thank you, and may God bless us all.